It's time now to talk about the linear equations that we were dealing with in the last video and how they relate to the graphs that we were talking about. So remember that we talked about the Cartesian coordinate system, where we basically take two number lines and we put them in the plane and we make them perpendicular. So often, if we're using the variables x and y, then we put the horizontal line as x and the vertical line as y. Each of these are number lines. The horizontal number line counts upwards to the right, and the vertical number line is going to count upwards as we go, well, upwards. And the idea here is that we can locate points on the plane by saying how far are they in the x direction, or in other words, what point are they at along this line and what point are they along vertically. It's kind of like giving directions by telling somebody the intersection if you live in a city that has everything divided up into blocks. So for example, this point right here would be the point 3, 1, because we are directly above 3 along the horizontal axis, and we are directly across from 1 on the vertical axis. Now, what I want to talk about today is I want to go back to the linear equations, which remember that a linear equation in general is something that looks like ax plus by equals c. This, by the way, is called the standard form of a linear equation. And I want to think about what would the graph of something like this look like. Well, when we see what this graph is going to look like, it will also explain why we call these equations linear equations. So let's think about the possibilities here for this graph. And give me a moment here while I erase things. So the first possibility is that, let's suppose that we have b equals 0 in that standard form. Then what we really have is simply ax equals c. This means that x is equal to c over a. So any pair of the form c over a, comma y is a solution to this particular equation. In other words, it has no dependence on the value of the second variable whatsoever. Now, that seems a little bit weird, but it's a possibility. There are some situations in which you have two variables, but actually what you care about doesn't depend upon one of them. And really, this is kind of more frequent than you would maybe realize. I mean, if you're talking about, let's say, treating a dog, let's say, because, we're talking about veterinary stuff a lot in here. If I'm talking about treating a dog, there's going to, in general, be a lot of data that I have about the dog, a lot of stuff I know about the dog that doesn't affect my treatment. For example, it's usually not going to matter whether or not the dog has long fur or short fur. So we could measure, hey, what is the average length of the fur on this dog? But it's not going to actually matter to us when we ask how much medicine is this dog going to get. Anyway, so what would the graph of this thing look like? Well, the graph of this thing is going to look like any point in the plane whose first coordinate is equal to c over a, and the second coordinate can be literally anything. So what we're going to get in our graph here is we're going to find the point c over a, wherever that might be, and then our graph is just going to be a vertical line over that point. So this is the line x equals c over a. Again, the y coordinate here does not matter. The y value doesn't affect this equation whatsoever. So it doesn't play a role. So that's the first possibility. Now, the second possibility is very, very similar, but unfortunately I'm going to have to erase this because I don't have a lot of room to work on this whiteboard. So give me a second here as I clear some space. So possibility 2 is that A is equal to 0 in that standard form, in which case our equation looks like by equals c. Well, this just means that y is equal to c divided by b. In this case, we see something as similar here to what we saw in the previous case, the first case, except instead of x being equal to a fixed number and there being no dependence on y, here we have y is equal to a fixed number and there's no dependence on x. The x value can be anything. So anything of the form x comma c over b is a solution. So what would this look like if I wanted to mark off all of these points on the plane? Well, once again, I would get a straight line, except instead of it being vertical, we would find the point c over b here along the y-axis, and we would get a horizontal line. So this would be the line y equals c over b. So in the first case, we got a vertical line. In this case, we got a horizontal line. Now let's think about what happens in the third case, which is really kind of the most interesting case. So what happens if both A and B are non-zero? So case 3 is A is not equal to 0 and B is not equal to 0. What happens here? Well, in this case, let's think about this general standard form ax plus by equals c. Now, because of the fact that both of these are non-zero, both a and b are not equal to 0, I can rewrite this as by is equal to c minus ax, and I can then rewrite that as y is equal to c over b minus a over b times x. And I'm going to do something here to make this a little bit easier to write. I'm going to come up with some new symbols for these values. So I'm going to say, let's let little b be equal to capital C divided by capital B, and let's let little m be equal to negative a over b. I can do that. I'm just coming up with some new symbols to represent what's going on here. Then what I've really found is that y is equal to m times x plus b. So all I've done here is I've rewritten this equation using little b and little m like we were just talking about. So as long as my standard form has capital A and capital B both non-zero, then I can do this. I can rewrite this in this form. Actually, I can do this even if A is equal to 0. If A is equal to 0, then I could still do this. So really all I needed to do was say that B is not equal to 0. But for this case, we're interested in when both of these are non-zero. Now, I want to think about what would a graph of something like this look like. Well, there's a couple of things that we can say about what the graph of this thing would look like. So what are the solutions? That's really what we're asking. I mean, on the one hand, for any given value of x, you plug in this value of x, and you get y is equal to some number. So, for each x, we get one y that works. Because again, you take your value for x, whatever value you choose for x, and you substitute that value in here, and then you simply have y has to be equal to whatever you get when you multiply that value by m, and then you add this b quantity. So for every single x that I pick, any given value, I get some value for y that gives me a solution. And I get exactly one value for y that gives me a solution. I can't do multiple values here. But that doesn't really tell us a tremendous amount. Now, here is something that is going to help us out, something that is going to tell us important. Well, okay, I shouldn't say that it doesn't help us out at all. It does help us out some, but it doesn't really tell us what shape that thing is going to have in the plane. The next thing that I want to observe is that when x is equal to 0, then we get y is equal to m times 0 plus b. And that comes out to mean that y is equal to b. In other words, if I wanted to make a graph of what this thing looks like, and I'm going to make kind of a small graph here, so I hope you guys can see it okay. If I mark the point B here, my graph is going to go through that point B on the y-axis. So this is actually the point 0, comma B, if I want to write it out using its Cartesian coordinates. And I know that the graph of this equation is going to pass through that point. For this reason, we call B the y-intercept of the graph. The y-intercept just means where we cross the y-axis. So, that gives me one important piece of information that we can use when we want to make these graphs. Now, the next thing that I want to observe is the following fact. If I have an equation of this form, what is given x1 and x2, what is y2 minus y1 over x2 minus x1 if x1, y1, and x2, y2 are solutions? Okay, that sounds a little bit complicated. So let's break down what's going on here and make sure that everybody is really seeing why I care about this and why I wrote this down. So I'm going to pick two values for x, x1 and x2. And I'm just going to name them x1 and x2 because that way we remember that these are values for x and it's the first value and the second value that we care about. And then I want to know if y1 and y2 are the corresponding values for y that are going to give me solutions to this equation, this y equals mx plus b equation, then what is this difference in the y values divided by the difference in the x values? And we're going to look at what does that come out to be. Now, by the way, we often abbreviate y2 minus y1 and x2 minus x1 as delta y divided by delta x. This triangle is actually a capital Greek letter delta. It stands for difference, and we think of this as the difference in the y values divided by the difference in the x values. So what does that come out to be? Well, it turns out that we can actually compute that fairly easily. So unfortunately, I am going to have to erase this for a moment. We'll come back to this picture after we figure this out. So here's the thing that we can say. We can say that y2, after I neaten out my board a bit, y2 is going to be equal to m times x2 plus b, and y1 is going to equal m times x1 plus b. Okay, so what does that mean? Well, it means that if I write down this change in y, delta y divided by delta x, this is going to be equal to m times x2 plus b minus m times x1 plus b. And all of this is going to be divided by x2 minus x1. I'm going to erase this stuff too. I hope you guys have it down for notes. Otherwise, pause this. Make sure you have this written down. So what can we do at this point? Well, this looks like a bit of a mess, but fortunately, there's some stuff I can do to simplify this. I can rewrite this as mx2 minus mx1 plus b minus b, all divided by x2 minus x1. Now, let me get out of the way so you can see what I actually wrote down there. So all I've done is I distributed this negative sign and I reordered the stuff in this expression, okay? So take a minute and make sure that you follow what happened there. Now notice that adding b and then subtracting b, those are going to cancel each other out. And so what I've really got here is m times x2 minus m times x1 divided by x2 minus x1. But you'll notice that everything in the numerator is multiplied by an m. And so what I can do is I can factor the m out of there. I can use distributivity in reverse. And I can say this becomes m times x2 minus x1, all divided by x2 minus x1. Now, because the whole numerator is multiplied by x2 minus x1, I can cancel that with the x2 minus x1 in the denominator, and I get m, just m. Now, this is really cool and really important because what it tells me is that the change in y divided by the change in x is always going to be equal to m, whatever that m is. Now, for that reason, well, for a reason that we'll see more clearly in a moment, we call this m the slope of this linear equation, because it turns out, as we're about to see, it actually is a geometric slope. Okay, so let's take a look at how that works. What we found from that complicated little computation here is that the change in y divided by the change in x is always equal to m. Well, what does that mean in terms of our graph? It means that if this is some point on my line, and I don't know where the point is, but let's just pick a point and do a quick example here. It means that if I move from x1 to x2 over here, like this is going to give me this kind of right triangle here with a base of delta x and a height of delta y. Now, because this ratio is always the same, it doesn't matter where I put my x2. I can move this second point around, and the ratios of these sides of this triangle are always going to have to be the same. So if I came over here, I would have to make a triangle which is a similar triangle. In other words, all the angles in this triangle are the same as the angles in this triangle. If I brought my second point in closer here, once again, I would get a similar triangle, which means that all the sides have the same ratios and all of the angles are the same. But if all of these points lie on the vertices of similar triangles, then what that means is all of these points lie on a straight line. So this means that all solutions lie on a single line. Okay, you've probably seen that before, and you might think, well, that was a long way to say something that you already knew. But I think it's kind of important to see kind of the mathematical way in which we really prove that this is what is going on here, that these really do give us lines. So, What we just showed is that all the solutions to anything of the form y equals mx plus b, these all lie on a single line. And in fact, when you put that together with case 1 and case 2, what we really showed is that any equation of the form ax plus by equals c, the graph of this is going to be a straight line. It might be a vertical line, it might be a horizontal line, or it might be a sort of a slanted diagonal line, but it will be a straight line. And that is why we call these things linear equations. Now, we said that they're called linear equations, but how can you actually make a graph of these things? Well, in order to make a straight line, all I need to know are 2 points. Once I've got 2 points, I can go ahead and I can just put those points in the plane, and then I basically just connect them up with a straight line, and then I continue that straight line off in both directions. So, knowing now that this has a graph that looks like a straight line, all I have to do is find 2 points, put those points on the plane, and I can connect them up. So there are a few ways of doing this, and the first way that I'm going to tell you guys for doing this, for making these graphs, is the following. So if I want to graph ax plus by equals c, we can find y when x equals 0. Then we can find x when y equals 0. And then we're just going to mark those points and connect them with a straight line. So let me give you an example of doing this kind of thing. Let's suppose that I have 2x plus 6y is equal to 12, and I want to make a graph of this sort of thing. So, when x is equal to 0, I get that 6y is equal to 12, or y is equal to 2. When y is equal to 0, I'm going to get 2x equals 12, or x is equal to 6. So, if I want to make a graph of this line, I can mark off here that we're going to go through the point 0, 2, because when x is equal to 0, y should be equal to 2. And then we're going to go through the point 1, 2, 3, 4, 5, 6. We're going to go through the point 6, 0, because when y is equal to 0, x is equal to 6. And then all I have to do is I have to connect up these points with a straight line. And this gives me a graph of this original equation. The graph, this line, any points on this line are going to be exactly those points whose coordinates are solutions to this equation. This method of doing it, essentially what we do is we find the y-intercept, and then this point where we cross the x-axis is called the x-intercept. So just like with the y-intercept, where the y-intercept is where we cross the y-axis, the x-intercept is where we cross the x-axis. With this method, essentially, you're using those two as your 2 points, then you connect them up with a line, and that's all that you are doing. So let's take a look at another example of doing that kind of thing. Let's suppose that I want to graph 3y minus 5x is equal to, let's say that we want to do 9. So in this case, the first thing I'm going to do is I'm going to find the y-intercept. So I set x equal to 0. That gives me 3y is equal to 9, or y is equal to 3. Now I want to find the x-intercept. So that means I set y equal to 0. Now, I suggest that you pause this and see if you can find the x-intercept yourself. But here we go. Here's what we're going to do. We're going to set y equal to 0, so we get negative 5x is equal to 9. That means x is equal to negative 9 over 5. So that is my x-intercept. Now, in order to make a graph of this thing, I first, of course, need an actual set of axes here. So we're going to have 1, 2, 3. Here is my y-intercept here at 0, 3. And my x-intercept is at negative 9/5. So we're going to have negative 1, negative 2. Negative 9/5 lies over here. It's near negative 2, but it isn't quite at negative 2. So this is the point minus 9 over 5, 0. And now I know that this line goes through those 2 points, but I also know it is just a straight line. So I just have to put a straight line through those 2 points. This method will work as long as the constant over here is not equal to 0. What we just did will work, and we can always use this method to get a graph. The problem that happens is that if the constant on the right-hand side of the equation in standard form is 0, then what you would find is that the x and the y-intercepts actually occur at 0, 0, so they're the same point. And in that case, you can't use this method. So that is one downside to using the x and the y-intercept method. The other downside to using it is simply that it's not always the most convenient method to use. So next time we're going to talk about more convenient methods, but I do want to show you just really quickly what else could you do if for some reason this method failed. Like let's say that the x-intercept and the y-intercept came out to be the same thing. So for example, let's suppose that I have 3y minus x is equal to 0. Well, the problem is that when y is equal to 0, we get x is equal to 0. And when x is equal to 0, we get 3y equals 0 or y equals 0. So this means that our intercepts, which I'm going to abbreviate intercept just by INT, intercepts are both 0, 0. And that doesn't work. I can't graph a line given just 1 point. Through 1 point, I could make many possible lines because I could angle them in any direction I please. I really need 2 separate points in order to deal with making a line. Well, what I can do is just pick a second value for x and go with it. You know, we pick one at random. Doesn't really matter what. So, for example, in this particular case, I'm going to say, and I'm going to erase this down here because I want to leave this problem at the top here and work this out. So we know that when x is equal to 0, y is equal to 0. And then I'm just going to say, okay, let's pick, say, x equals 3. Well, in that case, what we get is 3y minus 3 is equal to 0, or y is equal to 1. By the way, the reason I picked 3 is because I saw from looking at this that it would make this come out nicely, because then I can divide everything through by 3 without getting any fractions. But I didn't have to pick 3. I could have picked any number that I wanted to as long as it's not x equals 0. I could have picked x equals 10. I could have picked x equals negative 4. It would have given me the same line in the end. I just picked one that was convenient. So now what I can do to make this graph is I can say, I know that we're going to go through the point 0, 0, and I know that we're going to go through the point 3, 1. Because when x is equal to 3, y is equal to 1. And now I have 2 points. I can make a line through those 2 points, and that gives me my graph. Okay, that is the worst attempt at a line that we've seen so far today. Let's see if we can make something that's slightly more of a line. Well, hopefully you guys get the idea. I am incapable of drawing straight lines, unfortunately, especially on whiteboards. I shouldn't say especially on whiteboards. I'm just incapable of drawing straight lines. So imagine that this line is straight, and yeah, it's supposed to be a straight line. So this method will work. You don't have to try to find the intercepts. Instead, you could just say, hey, I'm going to pick 2 different values for my x coordinate, see what y comes out to be, and those are going to give me 2 points, and I make a line through them. In fact, this method will work even if this constant is non-zero. You can still just say, I'm going to pick 2 values for x, solve for y, mark those 2 points, and put a line through them. So that will work out for you as well. All right, now, that's still not always the most convenient way of making these things or of thinking about them. So what we're going to do next week is we're going to talk about how often, if you want to graph a line, it's really not the best idea to think about it in standard form like this. It's actually, there's some other formats for thinking about lines, some other ways of writing out those equations, which can work out nicer for you, especially when you're thinking about how do you graph these things. But in the meantime, so a lot of this stuff is not covered so well. I mean, there's some of this stuff in your book, but I'm also going to be uploading over this weekend some additional documents for you guys to take a look at on Blackboard. Some PowerPoints that I was able to get a hold of that they weren't really meant for this class, but I think that they cover this stuff about lines pretty well. Some of it is a little bit silly looking maybe, but they have the information in there, so I figured I would post them. You guys can look at them. Hopefully they're helpful to you. Otherwise, I will talk to you guys next week.